Good evening, everybody. This will be my final update for the Office Century, or my EET Capstone Project 2. Last time I gave you an update, everything was basically done. I needed to wrap up some finishing touches on it, house it in a box, set it up at my office. And so I've done that as of yesterday, or 24 April. I hooked it up in my office and plugged it in all day and let it run, and it's been running ever since. So, this project has been a very reliable device to gauge if there are any intruders trying to sneak up on me. The Office Sentry has accurately detected when somebody breaches that exact right position in my office, or the threshold, and sets off an alarm that blinks, or the LEDs. So I know when they're there. It will also, as you've seen, display an LCD across an LCD how far away they are in feet and inches. So with that, I'll get into the outline, which are the materials used. The sketch and the code haven't changed, but I'll show you those guys too. Added in some calculating of the distance and determining the distance. I will show you the video of it being hooked up at my office, and then we will end with some references. So, what did I use? I used a Arduino Uno. I used a ultrasonic sensor. Ended up using 2 high-intensity LEDs, LCD screen, power supply module, a 270 ohm resistor, a 10 ohm potentiometer, a NPN transistor, a magnetic money clip for the ultrasonic sensor. You'll see how I use that. A ATBU enclosure for the LCD screen, and I used a box to house the whole thing that I had laying around, just an old Amazon box. And to power the circuit, why I use the power supply module is so I could plug in an adapter plug into the 35mm jack, and that way it could just be plugged in all the time. So, here is the sketch of my circuit. Nothing has really changed from this, except I added a second LED, sorry about that, a second LED to kind of get my attention a little bit better. Yeah, so that's what I got for that. Alright, so calculating distance. This is something I added in. The ultrasonic transceiver module used sends out pulses at a frequency about 25 kilohertz and listens for the echo with a microphone. If there's something for the signal to bounce off, the system receives the return echo and tells the microcontroller a signal has been received, and to calculate the distance. For the Sentry, I placed it on the side of my desk, and the signal is sent out to bounce off whatever crosses the path. So to calculate the distance from the ultrasonic transceiver, the Arduino measures the time it takes for the signal's round trip from the transceiver to the target and back. So for example, I used the Arduino measures a time of 10 milliseconds. So you would calculate that by what I have there at the bottom, and how I got the 1,120 feet a second is that the speed of sound travels at approximately 1,125 feet per second. And then you calculate distance by distance is equal to speed times time. So when you do that, you get 11.25 feet. But remember that the signal is traveling to the object and then back to the microphone. To get the correct distance to the object, you have to divide by 2. So if the controller measures 10 milliseconds, then the distance to the object would be 5.625 feet. If there is an object for the signal to bounce off, the microphone picks up the reflected signal. The Arduino marks the exact time the signal is sent out and the time it is received, and then calculates the delay. So hopefully we got that. So determining the distance. So the range of the transducer is approximately 10 to 12 feet. The returning signal is always a lot weaker than the transmitted signal because of some of the sound waves energies that dissipate through the air. But if it detects an echo, it will determine the distance, the microseconds, between the send and receive. So for inches, it is inches equals time divided by 2, all divided by 74 microseconds an inch. How did I get 74 microseconds an inch? Well, we take the speed of sound, which is 1,125 feet a second. We times it by 12 inches, which will give us 13,500 inches a second. We divide we take 1 second divided by 13,500 inches, and we get approximately 74 microseconds an inch. So, for it to display inches, we take the time, divide by 2, all divided by 74 microseconds an inch. For feet, I did the same thing, except I times it by 12. That puts us back into feet. And then we, of course, we divide by 2 because of the echo itself. So, with that said, here is the final video for my project. And this is just a video or a picture of what it actually looks like. So you can see I just have it housed in a box. The tape's holding the flap together, but it's plugged in to the outlet at the bottom underneath my desk. I have it all taped in there. I have the potentiometer already set up for the correct distance to the threshold that you can kind of see, and that's where I actually use it's actually an old wallet, and I put the transceiver in there. So right here I'm showing you that it is detecting that there is somebody there. It goes to 9 feet, which is approximately where my boss is standing, but it's not blinking because I don't want it to blink unless somebody crosses that threshold, which is what you just saw it right there do. It's kind of hard to see the LCD screen with the video, but it still only goes off at about 50 inches is what in my previous video I showed. So it's still picking me up. I'm at 7 feet there, 6, 4, and it's at 52 inches where it's blinking, but it hasn't updated. So it's hit 646 there. This next little bit, I wanted to see if it would pick me up if I kind of bolted across. See if it would pick me up with a quickness, and it actually did. I was pretty impressed with it. So that was the video for that. I have my update 2 video and my proposal. The last thing I wanted to obviously show you guys is that the sketch itself, the code itself didn't change. It's still here. I don't need to bore you by going back through it, I don't believe. So there's that, and here are the references I have. Thank you guys very much.